I'm PW Crack, pen tester at Warcaller, DEF CON Goon, kind of a crypto nerd. Jesse?
Hi, I'm Jessie. I'm a mathematician by training, and I do cybersecurity for fun, I guess. I do have a job, I just don't want to say where. And then I am also a DEF CON goon, and I make a lot of puns and jokes, as a lot of people in the audience already know. So this is going to be a very fun. Okay.
So warning, we're going to talk about a lot of math. So you have been warned. So first, let's talk a little bit about symmetric versus asymmetric cryptography. Symmetric cryptography, we create a key, we encrypt something with that key, we decrypt the same thing with the same key. In asymmetric cryptography, typically known as public key cryptography, we create a public key and a private key. We encrypt something to the public key, we decrypt it with the private key. Typically, in signing, you do it the opposite way. And that's a little bit less efficient. It's slower, it's more complicated. So typically that is done in larger crypto systems to send the symmetric key. So you use asymmetric cryptography to encrypt the symmetric key, and you just send that so that your message is still encrypted with the symmetric key, and just send it back and forth. So let's take a short diversion about symmetric cryptography. If you have a random string of characters and you XOR those with your message, you still get a random string of characters. This is the basic principle behind one-time pad. It is provably secure. There are a couple of problems, though. You can only use the key one time. The key must be as long as the message, and so you'll need to figure out how to distribute the keys securely. That gets us back to the asymmetric cryptography. You can use a shorter key to generate a random stream or key stream and use that to XOR with the message. That is not provably secure, but is generally considered to be secure. So in asymmetric cryptography, we're going to identify a problem that is hard to solve in one direction, but easy to solve in another direction. So for instance, that would be factorization. We're going to create a private key and a public key, and creating those keys will be easy to do in one direction, but will create a problem that is very hard to solve in the opposite direction, for instance, factorization. And that's, so RSA is typically a system that's used for that. Right now, a lot of crypto systems would use elliptic curve because it's more quantum safe, but traditionally, RSA has been a public key, private key system or asymmetric system that we would use to do that. So I asked Jesse, so Number Field Sieve, the most efficient way to factor an RSA key is a number field sieve. That would be the most efficient way to factor a very large prime number. So I want to see how that would work. So I asked Jesse, hey, why don't I have a number field sieve.py on my laptop? Now, not that we're practically going to be able to factor a very large number, but it would be good to see in code how one would do that using the most efficient way, right? So, hey, Jesse, why don't I have number field sieve pi on my laptop?
Bob, that is a really good question. The best talks start with seemingly innocent questions. So that really was the start of it, was he came to me and he's like, you know, I keep reading about this number field sieve, and I'm into cracking passwords and figuring out how to break things down, and I know how all these encryption schemes work, but I don't actually know very much about this number field sieve. And I keep hearing that I need a PhD mathematician to help me with that, and I happen to know one. So we are going to spend some time digging into the number field sieve, and I really appreciate PW Craig for coming to me and asking me about this problem. This is Bob the Builder. For those of you who don't know, I actually did try to Photoshop Bob's face onto Bob the Builder, and it looked so creepy. So I decided not to do that.
I should have got a hard hat.
Yeah, I'm sure I've seen some floating around. I'm sure somebody would have let you borrow. Okay, so thanks for the introduction and the background. Here's a little bit of an outline into what we're going to talk about today. So I'm actually first going to go through a little bit of history of integer factorization. There's quite a lot there mathematically. A couple of slides on the status of factorization. You mentioned already that the number field sieve is probably the most efficient algorithm for factoring large semi-prime numbers. We'll talk about the situations in which that's true. There is going to be a little bit of math. We're going to talk about that. And then we will build up to the general number field sieve through working with the quadratic sieve first. And then, if I have time, we might even do a demo. So we'll see what we can get through today. To be clear, there are years of mathematics into these algorithms, and I'm trying to condense what I can into a 1-hour talk. So we'll see what we can get through.
Does anyone else have a math PhD in the room?
I was going to ask, does a ring homomorphism mean anything to anyone? Okay, all right, nice. Great. Don't judge my algebra, please. I am a mathematician, but I'm not an algebraist. Okay, so let's get started. A little bit of a disclaimer. I've already talked about how much math goes into these algorithms. The goal of this talk is not for all of us to walk away an expert in the number field sieve. The goal of this talk is for everyone in this room to potentially have a better understanding and appreciation for why factoring large numbers is very hard. Maybe some of you will see the math that I present and think, man, maybe I did just have a really shitty algebra teacher and math is actually pretty cool. That would be a huge win for me. So if at the end of this, no. Mubix, no. So if at the end of this, y'all are like, maybe I should go and look up more math stuff. Honestly, that's a win. No. Mubix, stick with me on this, okay? Okay. So let's go over some history, and PW Crack, jump in if there's anything you'd like to add at this point. There was a pre-computer era to factoring large numbers. We started in about 300 BC with the sieve of Eratosthenes. How many of you guys have heard of Eratosthenes? Now, he has this sieve, but he's actually more famous for something else. Does anybody know what else Eratosthenes did? So Eratosthenes was the first person to accurately measure the circumference of the Earth. Yep, and I'm sure somebody before Eratosthenes was like, it's greater than 5, but we don't count that. I actually do want to talk about the sieve of Eratosthenes very quickly. How this works is the most naive way to factor an integer that you could possibly think. I'm going to walk through every integer and I'm going to ask, is it divisible by any of the numbers I've already seen? If it is, then I mark it off. It's not a prime number. And then I keep going. So you start with 2. Is 2 divisible by any integer I've already seen? It's only divisible by 1, so it's a prime number. Is 3 divisible by any integer I've already seen? Well, it's not divisible by 2, so it must be a prime number. And then you just keep going and keep going. Believe it or not, this concept of just naively going through numbers is foundational to some of the more complex algorithms that we're going to talk about. So I wanted to make sure we all had at least a tertiary understanding of how sieves work. Around the same time, this guy Euclid came up with Euclid's algorithm, and I'm going to mention that very briefly. Euclid's algorithm is actually the way that we calculate greatest common divisors of two numbers. Calculating greatest common divisors is actually extremely easy to do. And a greatest common divisor is essentially, if you have two integers, you want to know if there's any number that divides both of them, and you want to take the biggest such number. We're going to punt to Euclid later because calculating greatest common divisors is much easier than factoring large prime number or large semi-prime numbers.
Or greatest common factors, right?
Greatest common GCF, GCDs.
Right.
Yeah.
That's going to come back later.
Right. Yeah. Euclid also was famous for Euclid's elements. He is the father of geometry. This guy Fermat, some of you may have heard of Fermat. He's known as a giant douchebag within the mathematical community for saying, you know, here's this theorem that I have, and I have this proof of it, but the margin isn't big enough for me to write it down, so good luck with that. Then it took a lot of mathematics for us to actually figure out that the theorem that he posed is true, but there's no fucking way he actually had a proof of it. Fermat squares, there's like a little equation there. We're going to talk about that a lot, actually, as we go through this talk. Then a whole shit ton of linear algebra happened. Does anybody know who that guy is? That is Gauss. I heard it. Yeah, so Gauss is the father of linear algebra. A lot of Gauss's work is actually what allows us to be able to run algorithms in our computers today. So Gauss came along. And then in 1926, so there's a huge jump here. In 1926, Lamer came up with this mechanical sieve. It's actually a work of art. This person came up with what I would describe as a rudimentary calculator that uses chains to actually factor large numbers. The largest number that this mechanical device was able to factor is a 28-digit long number. And they actually have examples of these in the Museum of Computer History out in California, so you can actually go and see them. So now we're into the post-computer era. So just to give you a little bit of a timeline here, ENIAC was born in 1945, although ENIAC was not constructed for factoring large numbers. Another algorithm called Pollard's row algorithm came about in 1975. Up until the Quadratic Field Sieve, this was the most efficient algorithm for factoring large numbers, and it got up to a number that was about 78 digits long. And then in 1981, there was a huge development. This guy called Carl Pomerantz developed the Quadratic Sieve. And as soon as we stepped into more number theory with the Quadratic Sieve, the gates went wide open. And his paper is actually what's going to motivate most of the talk today. In 1982, RSA 129 was issued. Now, RSA challenges, if you've heard of those, they were challenges issued to the community to try to factor and figure out efficient methodologies for factoring very large numbers like semi-prime numbers that appear to be prime. The Quadratic Sieve was developed in 81. RSA 129 was issued in 82. It turns out that the Quadratic Sieve was actually used to factor 129. We'll get to that in a second. And then the Quadratic Sieve was generalized to the Number Field Sieve in 1988. 1994 was when RSA 129 was ultimately factored using a Quadratic Sieve. And then somebody asked, this guy Peter asked, you know, we have these theoretical quantum computers. We've hit a lot of our limits with traditional computing. Can we use quantum computers to actually accelerate our factoring of these numbers? And it turns out, sure you can, using Shor's algorithm for quantum computers. And this was before quantum computers actually existed. These were all theoretical at this point. And it is very interesting to me that RSA 129 was factored in 1994, which was the same year that Shor's algorithm was developed. In 2001, we finally get a quantum computer that can factor 15. Yeah, let's go. We're making progress. In 2020, continuing with the trend, RSA 250 was factored. And then today, the most recent thing I can find is that theoretically, quantum computers exist that can factor 39-bit integers.
IBM has a quantum computer lab online. You can go to the website, you can create an account, and you can run Shor's algorithm on an actual quantum computer. You can actually factor slightly larger primes than 15, more like 51. That kind of thing, but that's about it. But it actually runs on an actual quantum computer. You could do that yourself from home.
One other thing I want to mention before we transition into moving forward with with these algorithms is that even when challenges like RSA 129 were proposed, at the time they were viewed as such huge feats. Martin Gardner, if anybody's heard of him, he's a famous mathematical puzzle guy. He actually published an article in Scientific American at the time that said that with current state-of-the-art capabilities, they did not believe that RSA 129 would be factored for 40 million years. And obviously that did not end up being true, but it just is a testament to how difficult some of these problems have historically been. Okay, so I mentioned the status of factorization. P.W. Crack already mentioned that the number field sieve is the most efficient algorithm for factoring large numbers. But what do you mean by large, right? So yeah, we're going to get to the GNFS eventually, but it is extremely costly. So just to cover all the bases, I have a little table here that shows, what algorithm you should actually use depending on the size of your number. So I want us to remember that when we're talking about these algorithms, we're actually talking about very large numbers. So like 10 to the 100th power, like we're talking big stuff. Actually, in Python, Python does not natively have an integer factorization script or function. SymPy does, and just to prove the point, for numbers up to about 10 to the 9th power, it's kind of hard to see there, but 10 to the 9th power, they actually do just use a lookup table because that up to that point is actually the most efficient way. Okay, this is your last chance. Yes, D. How do I? Oh, no. I use Python. That's how I know. Yes. So if I'm interpreting your question correctly, you see growth in efficiency in factoring large numbers. It correlates with like Moore's law, right? And also the development of a lot of the mathematical tools that allow us to do that. But we are reaching a point of decline. Like we're not really getting any more gains. I'm going to talk about some of the math too. We are kind of at the point mathematically that unless there is a huge development in the field of mathematics, we're not going to get any closer, any more gains in factoring numbers. Yeah. Okay, again, this is your last chance. You can leave now if you don't want to see any mathematics. Okay, don't all go at once. Okay, modular arithmetic. Anybody know anything about modular arithmetic? Have you heard of this concept before? Even if you have not raised your hand, I promise you that you have. Here's a definition. We would say that two numbers A and B have the same remainder when divided by a smaller number n. If they do, they are congruent modulo n. And we write this with this, it might be a little hard to see, but there are 3 lines here. It's not equality, it's congruent. So here's some examples. Again, we've all done this. We've all done this if you've used a clock. 21 is congruent to 9 mod 12. And if you look at the clock, using a 24-hour clock, you would use 21 for 9 p.m. But 9 is kind of ambiguous if you're using a 12-hour clock, right? So it could be 9 a.m., it could be 9 p.m. But if you use 21, then you know exactly what it is. All this is saying is that when you look at the clock and divide by 12, 21 and 9 have the same remainder, and it is 9. So as a test, 16 is congruent to what? Mod 12. Yeah, it's 4. Nice. All right, and there it is. Stated another way, if you take two numbers that have the same remainder and you subtract them, you should get 0. So 21 minus 9 is equivalent to 0 mod 12 because they both have the same remainder, and when you subtract them, there's nothing left. So that's pretty nice. I want us to also focus on this part here. So for any number a and any number n, if you take a and you subtract that modulus n from it, you should get two equivalent things. And I want us to think about this clock when we talk about this. When you subtract n, that 12, you're essentially taking that clock and you're doing a full rotation. And you should end up back exactly where you started. So when we're thinking about these numbers and we're subtracting and multiplying things, it really is just a shift in our head is how we should be thinking about this. That little fact, I restated it here. It's going to come up later. One more that I want to mention is related to multiplication in modular arithmetic. If you take two numbers that have, their remainders when you divide by n and you multiply them, well, that's congruent to just multiplying the remainders. And here's an example. So we're using our 16 and 21 from before. If we take 16 and 21 and we multiply those, we should get something that's equivalent to 4 times 9 mod 12. Remember, the 4 and the 9 were our remainders. 16 times 21 is 336. On the right side, 4 times 9 is 36, and I factored both of them down below so that we can see. The 28 and the 12 is 336. The 3 and the 12 is 36. Now notice that both sides are divisible by 12. So these are actually congruent to what mod 12? Because both sides are divisible by 12, so the remainder is going to be 0. That's right. So actually one more step here is because both sides are divisible by 12, these are actually congruent to 0 mod 12. It's okay if you're not following exactly. All I want us to think about is that multiplication kind of works the way that we think that it should in modular arithmetic. Okay. Now we're ready for building up to the GNFS. In mathematics, one of the most common tricks that we do, and I'm like pulling back the Wizard of Oz curtain here a little bit, is we see a hard problem and we say, damn, that's hard. Can we actually make this look like an easier problem? Because we're lazy, right? And sometimes you can. So when we want to factor a large number, obviously that's a hard problem. We want to make it look like something we know something about. So let's take this example, 8051. I'm telling you right now that 8051 is a composite number. Let's find its factors. I'm going to pause for 1 second just to see if anybody can see the trick. I'm looking at Frank. I'm just going to pause for 1 second. It's okay if not. Okay, I'm seeing some of this. All right. So it turns out you can write 8051 as 8100 minus 49. Now does anyone see the trick? Okay, I'm seeing a couple more head nods. Turns out 8100 minus 49 is 90 squared minus 7 squared. And this is a difference of squares. And if you do remember anything from algebra, you can write it like this, right? Okay, all right, now we're following. This is a cool little trick. And that gives you your factorization, all right? So we needed to see a little trick there in order to transform this factorization problem into an easier problem. All right. Now, you might ask, wow, Jesse, that's a cool trick. You can't always, well,
Wow, Jesse, that's a cool trick.
Can you always do that?
Can you always do that?
Turns out you can. If you have an odd integer and it has this factorization, you can always write it like this. And you know who proved that? This Fermat guy. Remember those Fermat squares I talked about earlier? Now he's popping up and he's starting to see these tricks, right? Turns out you can always write an odd integer in this form. And when you do, because of this difference of squares, you actually can explicitly find those factors, okay? Cool little trick, right? This is cool. So then if you really want to factor a number n, and you can write it in this way, we know that you can, then instead of finding these factors, we really just need to find this a, for which a squared minus n is a square. Because as soon as we have that, we can just write it as a difference of squares, and then we're done, right? So we need to just find this a. That's really what we're looking for. So we've transformed our factorization problem into a different one, right? Remember that clever trick. So in our previous example, n was 8051, a is 90, and b is 7. And this is just walking through the math. So with your a here, you get b squared, which is 7 squared, which is a square, and that's exactly what we wanted. So really, instead of finding the factorization, we just needed to find 90. That's all we needed to find. And then using the previous formulas, it works out exactly like it did. And Fermat's like, yes, queen, let's go. All right, this is excellent. I can always do this. This generalizes. We're done. Factoring large numbers is easy. But that only gets you so far. Now we have to punt to one more even cleverer trick. Instead of trying to find these numbers where you have equality, what if instead they were congruent to 0 mod n? So we're going to generalize just a little bit. And I'm skipping a little math here, but I want us to try to develop some intuition for why this matters. If you have this difference of squares that you can write this way, and it's equivalent to 0 mod n, and if it's 0, that means n divides it, right? There's no remainder. Neither of these things are divisible by n on their own. So if the difference that you can write this way is divisible by n, but neither of the two parts are divisible by n, that means n has to be split up into both of the pieces, right? So part of n is going over here, and part of n is going over here. And then when you multiply them together, you get something that's divisible by n. Aha. Our whole point was to factor n, right? So using this modular arithmetic trick, where when we combine things together, we might be able to get closer to a factorization, right? Okay. And remember, I mentioned Euclid's algorithm. It turns out actually that not only do you split n in this way and get a factorization, it's the greatest common factor. Again, I'm skipping a little bit of math here, but I already mentioned that finding the greatest common factor is easy. So again, mathematics, we're punting to even easier problems, right? I just want us to pause and make sure we kind of understand a little bit of this intuition. That if you have something that's divisible by n, but neither of the two pieces are, n's going to be split, right? Does that make sense? Okay, I'm seeing some nods. All right. We're going to keep going. All right. Yeah, Euclid. Euclid's like, GCF, say less. I got you. All right. So in that previous example, we're working with the same example. A and B were easy to find. They were 90 and 7, right? Let's try it in a different case because we really want this to generalize, right? So let's take n to be 2041, and let's investigate that a squared minus 2041 equals b squared. It's the same little formula we were working with before. Remember, we just want to find that a. And we need for b squared, we need a perfect square over here, all right? So let's start digging. I made a little table for you. If a is 46, 47, all these numbers, we can plug it into the a squared minus n and get b over here. And we start seeing a problem, right? There are no perfect squares. Like, shit, dog, I thought this was going to be easy. We're not getting any squares over here. What are we going to do? Dude, that's cat. Not going to lie. But then, another really cool mathematician noticed a trick. All right, we're all about tricks. If you square 46, modulo that n, it's 75. 75 can be written in this way, all right? Just bear with me on this. 47 squared is 168. Mod 2041, you can write it like this, okay? And we can keep going. So here's four numbers. When you square them, you get these remainders that have these nice factorizations. Now remember I talked about a modular arithmetic multiplication trick earlier. Let's take all these things and multiply them. We have our remainders. We know the trick for multiplying these together, and we have their prime factorizations. Now, wouldn't you know it? When you take all the exponents over here of these prime factors and bring them together, by God, you get a square. And that's what we were looking for the whole time. Like, dude, Fermat's over here like, what the hell? I thought this was going to be easy. But it turns out that you just need a little bit of a clever trick, noticing that you can take all these numbers and multiply them together. So now we have an a squared is congruent to a b squared mod n. Oh my God. Guys, we're fucking done, actually. Because now all we have to do is compute the greatest common factor, which I said was super easy. And there's your prime factorization. So I'm skipping a little bit of math in the GCF part here, but you're going to have to trust me that this is the easy part. Fermat's like, yeah, I knew that. All right. There are two places where I pulled shit out of my ass. Finding those numbers that you have to multiply to get the square, and then factoring them to get a square on the other side, right? We're going to talk about that in a second. But I want to pause, because believe it or not, everybody in this room just factored their first number with the quadratic sieve algorithm, okay? So when I punched this, congratulations, into Gemini, who was helping me build this slide, these were the four pictures it suggested that I use for factoring a number using the quadratic sieve algorithm. Yep, so you're welcome. This is huge, all right?
The fingers look good.
What?
The fingers look good.
Oh yeah, the fingers do look good, actually. And the balloons do spell party. Yeah, that's a little questionable. Yeah, so apparently this is what Gemini thinks we should be doing in celebration of factoring a number using the quadratic sieve. Okay. We're going to recap this, and I'm going to actually, on the left side, I'm going to write this. The left side is actually how you would implement this on a computer. The right side is a recap of what we've done. So in a computer, you're going to choose a bound on this concept called smoothness. Now, in our previous example, these remainders are all writable in this way using small numbers, a multiplication of small numbers. We call that being smooth, if you can factor them in this way. Notice amongst the four of these, the largest one is 7. In our algorithm, in order to keep things bounded, we actually have to a priori tell it how far we're willing to go. So we tell it, don't look at anything higher than 7, okay? And then we want to find that sequence of numbers so that when we multiply them all together, we get all these smooth things that combine to a square. In our example, that was the 46, 47, 49, and 51. We find those prime factorizations, which in our example was very easy. It's like 3 times 5 times 5 and 2 to the third times 3 times 7. And then we want to be able to multiply those together to get a square, which we did. We factor and compute the GCF, and then we profit. This is literally the quadratic sieve algorithm, okay? Are you surprised that this works? I mean, I was. I have so many questions, right? So I did skip a lot of steps. There are a lot of special cases and optimizations. Actually, the Wikipedia page on the quadratic sieve algorithm talks about this in depth. and goes over them really well. It's a good read, especially if you want to sleep. But I talked about this B, these A's that you have to just get lucky and multiply them together and you get a square out of it. This is hard. I picked an example for which that was easy. Generalizing that for all numbers is very hard. You have to get really lucky. The whole reason this works is that these numbers that are smooth, that break down, are sufficiently dense in the numbers we're working. We're just lucky. Do you have a question? Yeah. Yes. No, actually. It's a beautiful algorithm. Yes, I know. Okay, if I have time at the end, I will show you how it works.
Yeah,
it's amazing.
I want to jump in on the greatest common factor. It seems like if I'm factoring a very large number, that's very hard. But if I have two very large numbers that share a common factor, it becomes very easy. So finding the greatest common factor between two very large numbers, super easy. So that is counterintuitive. I freely admit that. But I also want to interject at this point. There is a hack out there. You can run this against large sets of SSH keys. You download public keys from the internet. Rapid7 has a huge database of stored keys. And then you just take every key and match it up against every other key. And you will find greatest common factors if those keys have been poorly created or poorly chosen, which frequently happens if you have, for instance, cloud instances with limited entropy. And if you find that greatest common factor between two keys, you've now found the factor of each of those keys. You now have the private key for that. So that is a cool thing that you can do to SSH keys, again, which there are very large databases of. And by the way, maybe that would be a thing to do on an internal pen test as well.
Nice. I was looking to see if Goki was here because he asked me yesterday about semi-prime versus relatively prime. I keep using the word semi-prime. There are very large numbers that look prime, but they really aren't. A good example in small number world is 51, which you mentioned earlier. It looks prime. You look at that number and you're like, prime. No, it's divisible by 3. 3 times 17. Check it. Okay. And sorry, what? 5 and 1. So yeah. So actually, this reminds me. I was thinking about this morning. We have tricks for checking if numbers are divisible by certain numbers. For 3, you take the digits and you add them up. And it reminded me of that Nate Bargatze skit where they're like, well, how many inches or how many pounds are in a ton, sir? Nobody knows. It's like, well, how do you check if a number is divisible by 7,429,000? Nobody knows. Yeah, we can't just come up with rules for checking divisibility, right, for every number. It just doesn't make sense. There was a question in the back. Yeah. So, okay, if I can't hear, I couldn't hear, yeah, please repeat.
There we go. Okay, so first was, how did you come up with the modulo number? And second was, at least with a computer, couldn't it be fast enough to iterate over squares of B and combine that with the modulo to see if there's a perfect square on the A side?
So, okay, that's a good question. So the first 2 questions there. the first question was, how did I come up with the modulo number? So I assume you're talking about these. Is that these numbers? Oh, that was just an example I picked to demonstrate this purpose. I just wanted us to practice factoring. I wanted us to factor 2041. I just picked it to demonstrate as an example. That's the number we're trying to factor.
Okay, but if you then went through on B and you take 1 squared, 2 squared, 3, 3 squared, 149, keep adding it to 2041 and see if you can get something with a clean square root on the A side. That be?
So if I understand what you're saying, actually that operation is equivalent to this operation.
Right.
Because it doesn't matter if you look at it from the B squared side or the A squared side, it's not more or less efficient than doing it this way. Yeah. That's a good question. Was there another question? Okay, all right. Oh, yeah. I don't know if you're done in your existing question. Nope. Okay. I have plenty more. Oh, okay. Well, I'll just let you go. Okay. All right. Okay. Blah, 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 blah. Party time. Yay. Okay. So, yeah. All right. Okay. I already mentioned this. Our ability to do this factorization depends on these numbers being smooth and being sufficiently dense in the numbers we're trying to factor over. And we're just lucky that it happens to be the case. And again, we just did the quadratic sieve. Okay, great. Why is it called the quadratic sieve? That's a good question.
Why is it called the quadratic sieve? Okay.
Right. Well, it's called the quadratic sieve because that polynomial we were working with is degree 2. Again, one of the most common tricks in mathematics is to use it, again, an easy example as a base case and generalize. Nobody said that polynomial had to be quadratic. Ain't nobody. We can take this and generalize it, all right? Now, I wrote this polynomial specifically in this way because it looks less scary. If I were to write it like this, people would have screamed. But this is actually the polynomial we're trying to work with. And we can make this as big of a degree as we want, actually. And the whole point of the general number field sieve is to not just solve it using a quadratic polynomial. We can generalize this to any degree that we want. And that's the whole point. Okay, so I'm going to go to this PDF real quick. I'm going to bring this up. Oh, no. I'm trying to factor things already. All right, it's off to the side, but you get the point. This was somebody's master's degree thesis from Virginia Tech, and it's an introduction to the number field sieve. He didn't even prove anything new. He just wrote up an introduction to it and got a master's thesis. I mean, kudos to that guy, right? So when we generalize, again, here he is talking about the quadratic sieve. Here's all the math, cool math. The motivation, we're going to generalize. Here we go. This is what this math starts looking like. I barely know what these words mean. We're taking these quotient fields and we're dividing by polynomials. Like, what the hell does that mean, right? But we can generalize. So I was trying to find, there was one page in particular. I'm not going to be able to find it on the fly, but that's okay. We're going to go back to where we are. Okay. The whole point being that once you generalize, though, out of quadratics, shit hits the fan. Okay. And then, again, I owe it to you to prove to you that this is more efficient than any of the other algorithms. It turns out, actually, that for the quadratic sieve and the general number field sieve, the number of digits of those, like, squares that we have to find, it's roughly n to the 2/3, where n is the number we're trying to, or the number that we're trying to factor. The quadratic sieve, it's like on the order of n over 2. When you generalize, you get into the 2/3, and it might not be obvious that that's more efficient. So here's a plot over time of those two charts. This one obviously is n over 2. So if this is basically how long it takes for you to run this algorithm, it actually looks like this n to the 2/3 is worse. Remember I said you don't want to use the General Number Field Sieve for small numbers? This is why. It's worse, but then look at how much better that is. N over 2 just keeps on trucking. And n to the 2/3 is way more efficient. So anyway, I just wanted to show you that. It really is more efficient, I promise. It might not be obvious, but it is.
Small. It's lookup table. It's that first chart that she had with the lookup table.
Yeah, it's
right?
on the order of yeah, right. If it's less than 10 to the 100, you're going to want to use something else. We really are talking about big numbers here. Okay.
And the original question was to understand this, like, let's see this in code. Like, I should be able to run this inefficiently on something small to sort of see how it's going to work and sort of see on my laptop how is this going to go.
Okay, so I know I'm running up on time. A couple more things. Circling all the way back to your original question, which was?
Can I run this on my computer? Where's GNFS.py?
Can we do this in Python? You can, but why would you? Would you write a web browser in Excel? Don't give the DoD any ideas.
It'll be next year's badge.
Right,
yeah.
right. Russ, where you at? Would you write Photoshop on a TI-83? And other fun questions we ask ourselves. So even in scientific Python is just C and Fortran under the hood, really. And there is no world in which you would want to run something as complex as the number field sieve just purely in Python. To prove the point, and again, I have a short demo that I can show you, but there was a picture that I was going to show. So this is Claude. All right, here's the real test. I'd really like to be able to run a Python script that uses the GNFS to factor a 90-digit semi-prime number. Can you do that big task? This is a great challenge, but I need to be honest about what's realistically possible. Even our AI know that this isn't a good idea. Full optimized GNFS implementation is extremely complex. Here's what we're talking about. And here's what I can do. I have some realistic options. And all the options are essentially is to write a Python wrapper around a bunch of other programs that you punt it to, and then it goes to those, right? Okay.
The Python part is run this.
Right, exactly. Okay, just a couple more things. Okay, so I'll pull up the code in just a second, but I definitely don't want to forget that I really, really appreciate PW Crack coming to me with this question. I would actually really love to walk through a mapping from the quadratic sieve into the general number field sieve for you. You have to take my word for it that if you understand the fundamentals of the quadratic sieve that we just walked through, you can understand the general number field sieve. You go through finding these squares. You want to multiply them together. You want to get something perfectly square on the other side. The trick is that, again, when you punt up to these polynomial fields, not as much is nice. And so you have to do a whole lot more work to get it to work out. And then I guess the last thing I'll leave you with is PW Crack. I did, get an implementation up and running using a Python wrapper. But actually, if you run, and I can give information about this, there's info in my slides. If you run this code, it actually shows you, it does a really good job of showing you, hey, I'm finding the polynomials I need to find. I'm factoring these. I'm looking in this space. It actually walks you through everything that it's doing, and it's super nice. So here was here are the 4 factors actually of the number that I asked it to factor, and it ran pretty quick actually. It's selecting polynomials and stuff. So yeah. So anyway.
That n was the number you were trying to factor?
Yes.
Okay.
I did actually try.
That ran on your laptop?
Yes.
Yeah.
And it ran in like, I don't know, let's see.
And we're still nowhere near an RSA 512, right? Like that's a big number, but it's not really big.
Right. Let's see. I was trying to see if it said how long it took. Actually, let me just.
The other thing I'll add on the RSA numbers is there will only be one answer, right? The original RSA number was created by choosing 2 primes. So once you factor it, you will have one of the 2 primes.
Yeah, so it's running. It took not very long for it to factor that number on this laptop, and just you can't see it, but this is one of those MacBooks with the touch bar, so that tells you how old it is. It's done. Yay! Yeah, any more questions? I don't know if we have time. But yes, they are. Yep. I know we answered some questions along the way. I really, really appreciate y'all hanging with me on the math part. Does anybody now want to go do math more, please? Okay, great. Yes, let's go. I really appreciate it. And you can find my contact information out and about. I'm on LinkedIn. Let's say you have a cool question like PW Crack. I'm happy to help you dig into it. Like, let's figure it out together. Yeah.
Yeah. So, from your perspective, what is kind of like the cutting edge of research on this? So I spent some time this year. I don't have a super deep math background, like an associate's in math, programming for 30 years. Read applied cryptography in the 90s.
Yeah.
And I was looking into some of like the Hamiltonian evolution stuff and doing like partial knowledge proofs of like quantum field theory, and not necessarily trying to find values, but trying to find locations of the factors. Like, what is happening in that space to your knowledge of like what is next?
Good question. So I'm not as in touch with the algebraic number theory area of mathematics as I probably should be. Most of the research that I'm aware of is happening in the quantum space, and that's a lot of functional analysis and Hilbert space theory, and there is some intersection, obviously, with number theory. But most of the research on the cutting edge, I think people are starting to realize again that unless there is a huge development in mathematics, we're kind of at our limit. It's going to take a big proof of a big theorem in order for us to get more efficient with something in the traditional computing space, I think. So I don't know. Ask Terence Tao.
If the problem is factoring the very large primes, that's all going to be quantum now, right? Shor's algorithm and how to engineer a quantum computer. The algorithm's done, the software's done, right? So that's fairly easy. It's now an engineering problem of creating a quantum computer. But at the same time that that's happening, everyone who's using these for cryptography is moving off of prime numbers and RSA. So they're moving to elliptic curve. So that would be the other side of that coin. Is like, we'll go figure out how to break elliptic curve in new, unique ways. What's the factorization equivalent of elliptic curves?
Oh, yeah, sure. Oh, sorry. Oh, he has the mic. Okay.
So for a Diffie-Hellman key exchange with modular exponentiation, is the modular exponentiation like the hard problem there that is difficult to reverse, or does that have anything to do with prime factorization? Or are they like, is it the same hard problem, or are they two different hard problems?
I actually don't know.
I don't know.
That's a really good question. Let me get back to you on that. We'll circle back. Somebody over here had a question. Okay. We can take it offline or something. I don't know. Jim's kicking me off. Can we start with living in a country that respects and honors our teachers? Yeah. All right. Anyway, I got to go. I'm happy to
Thanks
take
for
other
coming.
questions. Yep. Thank you.